All right, class, welcome back. We're on page 203 today. They want us to answer the following questions. So here's a simple equation. There's one unknown or one variable. They want us to find one solution. If we subtract 2 from both sides, we get x equals 8. All right. So before we move on, there's only one unknown, so we'd expect one solution, which is just one number. If we look at the real number line, there's 0, 3, 4, 5, 6, 7, 8. There's 8. That's our answer, right? This one, number 2, however, we could rearrange this by subtracting x from both sides. All right, this has two unknowns, one equation with two unknowns. So putting it like this, we're putting it in slope-intercept form, right? We could draw a line, and this line represents all the solutions. If we plug in a 0 for x, we have y as 5. So 1, 2, 3, 4, 5. So this coordinate here, 0, 5, that's one solution. But this is the equation for a line. We see here that the slope is -1, so every time we go down 1, we have to go to the right 1. So this line shows you all the solutions. There's an infinite number of solutions to this equation, and they all look like xy. It's a pair of numbers that satisfy this equation. 2 and 3 works. 2 plus 3 is 5, right? 1 and 4 works. We already did 0 and 5. This point right here would be 5 and 0, because 5 plus 0 is 5. So this is two unknowns in one equation. So the solution is a set of coordinates that happen to fall in a line. Let's look at number 3 here. So check this out. This one, there's two equations, and there's two unknowns in each equation. All right. This one is the same one we had a while ago, right? It looked like this, that line. But this is also a line. And let's see, if we subtract 2x from both sides, we would have y equals 2x minus 1. So this line, if we graph it, if we put 0 in for x, we're down here, a slope of 2. So this line looks like that. So to satisfy both of these equations, there's only one point, this coordinate right here, where the lines intersect. So again, the first line gives you this, the second line gives you that, but the only place where both the equations are true is right there where they intersect. So this thing has one solution. There is only one solution, and it looks like this, x, y, but there's a specific x and a specific y that work. So in order to figure out what this point is, where they're both true, what we're going to do is we're going to substitute. We're going to take one equation and basically stuff it into the other equation so that we end up with a new equation that only has one unknown variable. Again, we saw that this said y equals 5 minus x. Take what y is here and plug it into the second equation. So you'd have a 2x minus 5 minus x equals 1. got to be careful because you got a minus here, right? We're replacing y with 5 minus x. So we get a 2x minus 5, a minus minus is a plus x. 2x and 3x, 2x and x is 3x. Add 5 to both sides, you got 6. We got x equals 2. So notice when we plugged this in, we took y in terms of x and plugged it in, and that gave us a new equation with only one variable. Now that we know what x is, we can plug it in up here. Y is 5 minus x. Well, we found x is 2. So 5 minus 2 is 3. So our solution here is 2, 3. That's what that coordinate is. 2, 3. All right. Give me a couple of minutes, folks. My baby girl needs me. Come in. What's that? Daddy. Maddie, you want to watch her for me? Sure. All right. She's awake and needs attention. You want her swing? I'll bring you her swing. Okay, I'm back. All right, so again, this number 3 here, they give us 2 equations, 2 unknowns. Each equation has an entire line of solutions, but the only place where both equations are true is where they intersect. And the way you find that out is you take one equation, you substitute it into the other equation, so you can get a new equation that only has one variable. And once you solve for that variable, we solve for x, we can plug it into either one of the equations above to find out what y is. All right. They want us to match the equivalent equations. All right. These 2 equations up here, they're what we call independent, meaning they're not the same equation. If you take an x plus y equals 5, this first one, let's say you multiply both sides by 2. All right. This is the exact same as this. The solutions are the exact same. If you graph them, you get the same line. So these are not independent. These are what we call equivalent equations, meaning they have the exact same set of solutions. So if we're looking at these, we want to pair these up with their equivalent equations. Hey, Maddie, keep it down. All right, let's see. So like this one here, let's see what we could do with it. If we look over here, let's see. This, the 6 is half of 12, right? And we have a negative between the y and the x. If we look over here, let's see. 6 is a half of the 12. See, 3 is not half of 4. The coefficient for the x and the y here are the same. I'm not sure. Let's check out the next one. See, if we divided, well, if we divided everything by 6, we would have y minus 2x equals a negative 7. right? If we took everything divided by 6, that looks just like this one, right? If we added 2x to both sides, we have the exact same one here. So this goes here. That one's A. Those are exactly the same equations. They have the same set of solutions. If we look at B here, the x and the y have the same coefficient and the same sign. They're both positive. So here they don't, here they don't, but here they do. The x and the y both have a 1 and they're both positive. So that's the one I would look at. If we took this and divided everything by 3, we would have an x plus a y equals 6, which is indeed that one. So those are exactly the same solution, same equations. Now let's look at C here. The x is 3 times the y, but the x is negative, y is positive. Basically, they have opposite signs. These, they have opposite signs, and this one, they have opposite signs. So it could be either one. But again, the coefficient in front of the x is 3 times that of the y, which looks like this one. So yeah, if we multiply both sides of this equation by a -1, we get exactly that. So that one is C. So of course we know that one has to be D. Let's figure out how these are equivalent though. This says a 3x, right? This is a 3 abs x. We multiply both sides by 2, we get that. Yeah, which is exactly that. So any questions about this? Put your headphones on, Maddie. Yeah, we don't need to hear you on speakerphone. You're not that important. All right. All right, this is easy enough. Multiply each equation by the given constant. Multiply this equation by 7 on both sides. 7 times 3x is 21x. 7 times a -2y is a -14y. And 8 times 7 is 56. And number 6 here, multiplying everything through by 3. 2x times 3 is 6x. -1/3 times 3 is a -1. And 9 times 3 is 27. Number 7, multiplying through by a -5. 4/5 times a -5 is a -4. -2 times a -5 is 10. And -8 times a -5 is a +40. So multiplying everything in here by 2, -3 times 2 is a -6 over 7 x. 2 times a -y, and 2 times a -8. So again, this equation and that equation are the exact same equation. If they have the same set of solutions, they're logically equivalent to one another, in which case you would put that symbol in between them. That symbol means if and only if, or logically equivalent to. It's like an implication going both ways. All right, 204 here. Y'all ought to be pretty good at this by now. Solving for y. All right, if we divide everything by 2, we get that. If we divide everything by a -3, we get that. Here we'll subtract 2x from both sides, and then divide both sides by 3. We get a -2/3 x plus 5. Basically, you're putting these things in slope-intercept form. Subtract 3x from both sides. Divide both sides by -3. Subtract 2x from both sides. Divide both sides by 2. Multiply through by -1. Okay. We'll subtract 1/2 x from both sides. Now we'll multiply both sides by a -3/2. 3 over the 3 and the 2 over the 2 and the minus go away. We have y equals, multiplying this by -3/2. 4 times a -3 is -12. And then -1/2 times a -3/2 is a +3/4. And of course, we can take 12 halves and write that as 6. So here, subtract 4/5 x. Now multiply through by -1. Just +4/5 x minus 10. Subtract 1/2 x. Now divide both sides by 2. You okay, Maddie?
Yeah.
You need to give her a bottle?
Yeah.
You know how to make one? Here, I'll help you out. Hold on, folks. I'll be right back. All right, Mom, I'm gonna be home soon. So you sit and play Fortnite and be on the phone with your friends at the same time.
You know what? Just hand me the bottle once you're done with it. Yes. Thank you.
You're doing great, Maddie. All right, sorry about that. All right, for each scenario, identify the 2 unknowns, assign them variables. The first one is already completed. So these are going to be fun. Word problems. They've already done half the problem here. So a test has 20 questions, and they are worth a total of 100 points. The test has fill-in-the-blank questions that are worth 3 points each, and multiple choice questions that are worth 11 points each. How many multiple choice questions are there? So the 2 variables they give us, x and y. All right, x they have is the number of fill-in-the-blank questions. There's 2 types of questions, fill-in-the-blank and multiple choice. So x and y are the number of each of those types of questions. There's a total of 20 questions. So that tells us x plus y has to be 20. All right, the number of fill-in-the-blank and the number of multiple choice add together to give us 20. Now we need a second equation that's independent of this one. So what we do know is the test is worth 100 points. Well, we know the fill-in-the-blank questions are worth 3 points each. So if we take 3 times the number of fill-in-the-blank questions, and then we notice that the multiple choice are worth 11 points each. So if we take 11 points times the number of multiple choice questions, this is the total number of points, and it should add up to be 100. So we got two equations here with two unknowns, which means we should be able to solve for them. So since they both have an x and a y, what we need to do is make one equation that only has an x or a y. So if we take this first one and we just rearrange it so we have y equals this, we could take this and cram it right there. And what that'll do is it gives us an equation with only one variable. There's only an x there now. So now we can solve for x. Once we know what x is, we can plug it in here and we know what the y is. So we have a 3x. 11 times 20 is what, 220? All right, and then minus 11x. All right, you got to distribute appropriately, right? We're replacing y with this whole thing, so that's why you have to have these parentheses here. 11 is being multiplied by the y. That's our y. So 3x minus 11x is a negative 8x. 100 minus 220 would be a negative 120. So, oh, I lost my file. What is 120 divided by 8? 120 divided by 8. 15. X is 15. So now that we know that there's 15 fill in the blank questions, and we know that x plus y is 20, right? Or y equals 20 minus x. Just plug that in right there. 20 minus 15 is 5. So there's 15 of these and 5 of those. So there's two pieces of information here, the number of questions and the number of points. And we use them to create two independent equations of two variables, and we solve them, right? Graphically, you could graph these both, put them in the form of slope-intercept, graph them, and then look for where the lines intersect, right? Each one of these is a line. Where they intersect is at 15, 5. All right, so the solutions to the two equations is 15 and 5. Let's knock out one more here. All right, we got a nurse, and he or she is ordering two different kinds of medicine. Medicine A costs $7 a gram. Medicine B costs $9.75 per gram. The total bill is $268.50, and a total of 66 grams are ordered. How much of each medicine is ordered? So what we'll do here, since they're asking how much of each medicine is ordered, they're already telling us what the variables are. Instead of x and y, let's use A and B. A is grams of A, and B can be grams of B, right? Medicine A, medicine B. So that's what we want to solve for. That's what they're asking for. So we need, since we have two unknowns, we need two equations. All right, they tell us A costs $7 a gram and B costs $9.75, and they tell us the total bill. So if we take $7 times the number of grams of A and $9.75 times the total grams of B, we should get $268.50, the total price. We also know a total of 36 grams are ordered. So if we take grams of A and grams of B, it should add to be 36. Okay. Let me put this one first. So again, the trick here is we want one equation with one unknown. So let's take this guy and rewrite it like this. And now let's take what A is and put it right there. So then we have an equation with only b in it. Right? You can solve for either one here. It doesn't have to be A. We could have solved for B. It doesn't matter. So we have 7. A here is 36 minus B. 975B. Let's see if 50. Right? So we multiply through 7 times 36. 252 minus 7B. 975B. 268.50. So 975B minus 7B gives us 275B. 268.50 minus 252 gives us 16.5. So B is 16.5 divided by 2.75, which is 6. Now that we know what B is, plug it in. A is 36 minus 6, which is 30. So A is 30 and B is 6. Okay. You can always check your work. Does 30 plus 6 equal 36? Yeah. And then you can plug the numbers into your second equation too. Make sure they satisfy that equation to check your work. So let's have a quiz here. This is what quiz number 23. And we are on page 204. So anything before 204 is fair game. Let's see, let's look at page 197 here. Solving other exponential and logarithmic equations. Maddie, would you turn that off? Throw your phone in the yard. 11-year-olds are so obnoxious. Okay. So, solve for an exact answer. Let's see number 9 here. You're number 1. And that one. All right, let's take 15 minutes. So 328, let's check here. See, 328, 15 minutes be 338, 340, 343. I just got an email from the administration wanting me to encourage y'all to register for the spring semester. So register for the spring semester. Apparently it's time. All right, number 1. All right. If we're going to get the x out of the exponent, there's 2 ways we could approach it. We could try to take log base 9 of both sides, you know, log base 9 and the 9 too, that would undo one another. Or what we can do is try to rewrite this and this as the same base. I recognize 27 here as a power of 3, right? 9 here is 3 squared, right? And 27 is 3 times 3 times 3. It's 3 cubed. When you have an exponent to an exponent, you multiply them. So now when you have two sides of the equation and they have the same base, this tells you that the exponents are equal. We could see that by taking log base 3 of both sides. So the log base 3 and the 3 to the would undo one another. We have 2x equals 3. You can go straight from this step to this step. All right, that was a trick we learned in class. If you get the base is the same, then the exponents have to be equal. So if 2x is 3, then x has to be 3 halves. Of course, we can check our work by going to Wolfram Alpha. And just type in here, solve 9 to the x equals 27. I think I have to put a comma here, comma, for x. Real solution, x equals 3 halves. So we've checked our work, we know we're good, we can move on. All right, on the exam, don't just plug it into Wolfram Alpha and give me the answers. All right, that's not going to work. You have to show your work. I need to see that stuff. Okay. All right, let's look at this guy here. See, 6 is not a power of 2. How can we get this 3x out of the exponent? The other trick we learned, all right, sure, we could take log base 4 of both sides, and that would get rid of this, right? What would happen if we took log base 4 of both sides, though? That would undo one another, and we'd have 3x equals log base 4 of 6. That'll work as long as we leave our answer in terms of log base 4. But what we want is either a natural log or a log base 10. So what we're going to do here, let's just take log base 10, or the common log, because that's a button on the calculator. Not that we're going to use it, but remember what we learned about exponents and logs? You could take the exponent and put it out front. That's the way they work. And you can do that with any log whatsoever. We could do the natural log here. It doesn't matter. So what we can do now is bring this 3x out. So we have 3x times log of 4 equals log base 10 of 6. Okay? So x here is equal to log of 6. We're dividing both sides by that and that. So divided by 3 times log of 4. Okay? And since it asks for exact answers, we're not even gonna plug this into the calculator. This is our answer. Now you could have done log base 4. If we'd have done log base 4, we would have this. And it's still correct. It still works out. But just in case the person who gets our answer here might want a decimal, We'll leave it in terms of common log so that they can plug it into their calculator if they want. But again, they want the exact answer. That's the exact answer. If we plug it into a calculator, it's going to give us a decimal. So if we look at Wolfram Alpha, 4 to the 3x equals 6. So 4 to the 3 times x equals 6. So what does it give us here? It gives us common log of 2 plus the common log of 3 divided by 6 times log of 2. All right, if we plug this into our calculator and get a decimal and compare it to what we get, ours here, they're going to be the same thing. All right. So if you just use Wolfram Alpha and give me this answer, I'm going to know that you didn't actually work the problem, that you just plugged it in here. Okay. Because there's a ton of different ways you can work this problem. But if you're using the techniques that we've learned so far, you're going to come up with this or something close to it. Okay. As later on, you might learn what you can do with these. The log base 2, the log of 2 and the log of 3 would combine to be a log of 2 times 3, which is a log of 6. And then we have the 6 of log 2, which would be the same thing. Okay. But any questions about how we did this? You can use any log you want, but the trick here is you can move the exponent out of the log and multiply it, and that's what gets your x out of the exponent. Any questions? All right. Let's see. Okay, what page we're on? 204 maybe? Yeah. We're on number 20 here. So I want you to be able to solve problems like this, these word problems. All right, we have boxes of fruit. They can be purchased in large or small boxes. 3 small boxes and 14 large boxes are purchased for $203. And 11 small boxes and 11 large boxes are purchased for a total of $220. How much does a large box of fruit cost? Well, let's make one of our variables price of large box. And let's make our other variable S, price of small box, right? So they're asking us how much does a box of fruit cost, specifically the large ones, but we'll solve for both of them. So in day 1, they say 3 small boxes and 14 large boxes and how much they cost. So if we take 3 times the price of small boxes and 14 times the price of a large box, we should get $203. And on another day, they say 11 small boxes and 11 large boxes purchased for $220. Those are 2 independent equations with 2 unknowns. So we can do our same trick we always do. Let's do this. We'll have 3s equals 203 minus 14l by subtracting 14l from both sides. Now divide both sides by 3. S equals 203 over 3 minus 14 over 3l. I will plug that in over here for S. So we have 11 times 203 over 3 minus 14 over 3L plus 11L equals 220. All right, so we have one equation with only L in it, so we can solve for L now. So if we multiply our 11 through, 203 times 11, 2,233 over 3. And 14 times 11, 154 over 3. Plus 11L equals 220. Oh, I forgot my L here. All right, so let's combine our L's here. If we rewrite 11, all right, in terms of thirds, 11 would be 33 thirds, right? So just looking at our L's here, 33 minus 154 is a negative 121 thirds. L. That's going to be 220. Subtract that from both sides. Minus 2, 2, 3, 3 over 3. Again, if we're going to put this in terms of thirds, well, what we could do, let's just multiply this whole equation by times 3. We got a negative 121L equals 220 times 3, 660, 2, 2, 3, 3. Just to get rid of the fractions. All right, so negative 121L, 660 minus 2233, negative 1573. So divide that by 121. It's 13. So that's our answer. That's the price of a large box, $13. Now we know the price of a large box. We can plug it in right here and get the price of a small box. Right? So therefore, this is 203 over 3 minus 14 over 3 times 13. That's the price of a small box. Which would be, let's see, 203 minus 14 times 13, 182. So 203 minus 182 is 21 over 3, which is 7. So the price of a small box, $7. So 2 equations, 2 unknowns, substitute one into the other to get 1 equation with 1 unknown and solve for it. Number 21 here. The admission fee at a small fair is $1.50 for children and $4 for adults. On a certain day, 2,200 people entered the fair and $5,050 is collected. How many children and how many adults attended? Let's let A be the number of adults, and C be the number of children. Of course, you can use X and Y, but I like letters that actually represent what they mean. So, we need 2 equations for these 2 unknowns. Well, if we had $1.50 for children and $4 for adults, and they collected $50, well, if we take $1.50 times the number of children plus $4 times the number of adults, we should get $5,050. That's one equation. Now let's look at this other piece of information. How many people entered the fair, 2,200. Well, if you take the number of adults and the number of children, we should get 2,200. There's our two equations with two unknowns. Let's rewrite this one so that we could take A here and plug it in right there. And then we got 1.5c plus 4, 2,200 minus c, equal to 50, 50. Now we have one equation with one unknown, and we can solve. 4 times 2,200 is 8,800, and minus 4c. All right, 1.5 minus 4 will be a negative 2.5c. 50, 50 minus 8,800 is negative 3,750. So C here is negative 3,750 over negative 2.5, which is 1,500. We had 1,500 children. All right. We know that the number of adults and children is 2,200, or the number of adults is 2,200 minus children. 2,200 minus 1,500 is 700. So 700 adults and 1,500 children. Add them together, you get 2,200 people. Well, if we plug those numbers in here and here, we should get 50-50. Any questions? All right, moving on. All right, find one solution for x minus 3 equals 5. Add 3 to both sides, we have x equals 8. How many solutions are possible? Just that one. All right, graph this equation. 1, 2, 3, 4, 5, 6, 7, 8. There's the graph of it. It's that one point on a number line. Find one solution for x minus y equals 6. Well, let's put it in slope-intercept form. If we did that, we would have this. So our y-intercept is at negative 6. Our slope is 1. So it looks like that. How many solutions are possible? There's an infinite number of them. All right? Two numbers whose difference is 6. You could have a 6 and 7 and 1, right? 8 and 2, and so on. All right, graph it. There's the graph. Every point on this line is a solution to that equation. So a system of linear equations is a set of two or more linear equations. All right, this is a system of two linear equations with two variables. A solution is an ordered pair, x, y, that makes both equations true statements. So for this system, 4 minus 2 is a solution. There's only going to be one solution, and it's going to be an x and y pair. If you had, let me put it this way, ax plus by plus cz equals d, ex plus fy plus gz equals h, and jx plus hy plus kz equals L. All right, x, y's, and c's. If you have three equations with three unknowns, you can solve them, and there'll be one triple pair in x, y, z that will be a single solution to that set, set of three linear equations, okay? But this only works if these things are independent of one another. If they're not independent equations, then if these aren't independent, then they are the same line. If they're same line, then the set of solutions is that line. Okay, so we're going to start to delve into these. When you get systems of linear equations like this, there's techniques for solving them. Instead of just doing that substitution method, there's tricks that'll spit out the answers. Right? They all involve using matrices. Okay. If both linear equations are graphed on the same axis, all right, we see that each point at which the graphs intersect is a solution of both equations and therefore a solution of the system. Again, each one of these is a line, and where they intersect here, 4, -2, all right, that's the only solution that satisfies both equations. Okay. Later on, I don't know if we'll see it in here, but instead of two lines, you might have two planes that intersect. Two planes, you have a plane and then another plane. Let's see. Two planes would intersect along a line, okay? Or three, solid objects, like if you have a sphere, and a cube. Where they'd intersect would be a volume of space, okay? So what we're looking at here is the most basic approach to this kind of math, right? So a system of two linear equations, it either has exactly one solution, like this one where they intersect, no solution where the lines are parallel, or an infinite many solutions where the lines are the same thing. All right? So if they're on top of one another, every single point is a solution. All right? All right, matrices. Solve the system. Use the elimination method. I don't know what the elimination method is. Let's see if we can figure it out by looking at what they've done. So they wrote the two equations down. They got an arrow. And on the bottom, they rearranged this. They just solved for y, and they found that. How did they get y equals 2? Hold on. Let's see, if I took this guy, I added x to both sides, and I divided both sides by 3, y equals 1/3 x plus 1. Okay. All right, so remember last time how we took one equation, right? And we rewrote it so we could substitute it into the other one. The other thing that you can do is instead of substituting one equation into the other, you can add the two equations together to get a third equation, or you can subtract one from the other. So in this case, what they did is they took the second equation and they added it to the first equation. All right. So if you add all that together and keep it all nice in its column forms, right? All right. So they kept this first equation, right? That's the same as this. But what they did is they got a new equation by adding the second to the first. X minus x went away. It's a 0. 3y minus 2y is 1y. And then 3 minus 1 is 2. Okay? So this equation here came from adding these together. All right? So now they're keeping the bottom equation. Let's see, where did they get this x equals 3 from this? If you take this bottom equation, if you multiply both sides by a -2, you get a -2 times a -4, right? Now if you add these equations together, you get an x. Actually, let's multiply this by a +2. There we go. Now if we add them together, we get the x. The y's go away. That's why there's no y over here. And 4 minus 1 is 3. So we ended up with the two solutions. Okay, so you can take your original equations, you can add them together to get new equations, you could subtract them to get new equations. All right, and you add them together and subtract them from one another to try to make one or the other variable go away. Okay, see, at this point when we had y equals 2, we could have just plugged that in and done substitution. Okay, so this elimination method is where you add or subtract the equations from one another to get new equations that eliminate one of the variables. So if we graph them, let's see, what do they want? I'm guessing these are the graphs of these equations. Yeah, I don't know where they're getting these graphs. Let's graph these. X minus 2y equals -1. We have to, let's see. Yeah, we got to put it in the y equals mx plus b form. So if we do that, we got a -2y equals a -x minus 1. So y equals 1/2 x plus 1/2. Yeah, so there's our first one. Y equals 1/2 x plus 1/2. So that's the first one. Let's look at our second one here. 3y equals x plus 3. So y is equal to 1/3 x plus 1. So 1/3 x plus 1. So that's what they have graphed here, is these two equations. So what's going on over here? Let's find out. This y equals 2. Again, that's what we got that from adding these two together. It gave us that. That's what this line here is. That's y equals 2. All right. This line is the same as this one. So all I've done is graphed these two equations. So y equals 2. If we add one line to the other line, we get a new line. Y equals 2. Boom. All right. So if you take the y value of these and add them together, you're always going to get 2. Okay. There we go. Okay. And then once we had this y equals 2, we looked at this and we needed to eliminate the y's to get an x. So if we multiplied both sides by 2, we did that because if we add that together, that goes away and we got an x equals 3. All right, that's our elimination approach. So we have our x equals 3 and y equals 2. So those are our two solutions. Here's y equals 2. The line x equals 3 is this. So where they intersect is at 3, 2. Those two lines. All right, so in our elimination thing, what we're doing is we're taking this and we're converting it to this, right? They intersect at the same location, right? It's just a lot easier to find the intersection of two, a vertical and a horizontal line than two diagonal lines. So this elimination act, what it's doing, it's slowly converting things to horizontal and vertical lines. Let's look at matrix notation. Okay, you might notice that up here, we kept our x's and our y's in columns, basically. We keep our x's together, our y's together, and then the remaining coefficients together. All right, so what you can do is if you keep things like that, you can just throw away the x's and the y's. All right, and that's what matrix notation is. Instead of writing x's and y's everywhere, all right, you just write it like this. So you have a 1x and a negative x, so a 1 and a negative 1. You got a negative 2 and a 3, so a negative 2 and a 3. You got a 1, negative 1 and a 3, so a negative 1 and a 3. So these are your coefficients, right? The coefficients to your x and y's. That's why it's called the coefficient matrix. These are just constants. There's no variable. So this is your constant matrix, right? So following the steps from above, follow the steps from the above example, all right? So they combine these to just one matrix like that, okay? So basically you have like, that's like an equals there, okay? How did they get from here to here? They added that and that together, right? And replaced the bottom column, right? Remember, we added these two equations to get this new equation. So when you add 1 and a negative 1, you get a 0. When you add the 3 and the negative 2, you get a 1. When you add the 3 and the negative 1, you get a 2. So we added them together and replaced the bottom one with their sum. All right. Once we were there, how did they get here? They multiplied this all the way through by 2. And now whenever you add those, all right, you still get your 1. Your 2 minus 2 becomes 0. And your 4 minus 1 becomes 3. Okay? So we keep this old one here. We like to have the zeros and the ones. So what we have here is a 1 0 0 1 3 2. There's our solution. See, our goal is to turn this matrix into a matrix that looks like that has ones along the diagonal and zeros everywhere else. Okay? If you're working with 10 or say 4 equations with 4 unknowns, you'd want to turn it into this one. Basically zeros everywhere except for ones down the diagonal. That's the ultimate goal. They call that an orthogonal matrix. All right, so the number of rows is m and the number of columns is n. So this is a column, that's a column, this is a column. These are rows. So when they say an m by n matrix, all right, they're talking about columns by rows. Okay, and when m is equal to n, the matrix is a square matrix. We like working with square matrices. So this would be a 2 by 3. Wait a minute. Did I read that wrong? Rows is m. Yeah, I'm sorry. Rows is m. So we go by rows first, and then the columns is second. So this is a 2 by 2, 3 by 3. So again, the number of rows comes first, and then the columns is the second number. Sorry, I said that wrong the first time. Okay. Let's see what they say here. All right, the position of an element is designated by its row and column written as subscripts, a sub ij. For example, a sub 1, 2 refers to the element in the first row, second column. Okay, so a sub 1, 2, the first row, second column. So that's -3. Over here, a sub 1, 2, first row, second column. That would be a -2. Okay. So the goal of this section is to write linear equations of this form, 2 linear equations, or 3 equations with 3 unknowns, where x, y, and z are variables using their associated augmented matrices. So again, we got a 3, 4, -5, 3, -8, -1. So they might give you the equation in a different form. What if they give you 3x plus 8 equals 5y? You need to rearrange it so that you have your x's first, your y's second, and then what's left over on the other side of the equal sign. Then you enter it into your matrix. So here we have all x's, right? 4, 3, 4. Here's our y's. 3, -2, and the last one will be a 1. All right, plus z minus z 4c, plus 1z minus 1z, and a 4z. Okay, so first step is getting your matrix set up correctly. Then we'll get plenty of practice on how to manipulate the matrices to give us the answers. Right, this guy right here, there's 3 equations with 3 unknowns. All right, that means there's going to be one solution of the form x, y, z. This is a coordinate in 3-dimensional space. X, y, actually y, z. All right, so it's 3-dimensional space, right? Okay, so each one of these is a line. So where all 3 of these lines in 3-dimensional space intersects is the solution. Now, they might not all intersect at all, right? They all have to intersect in the same location for there to be a solution. So we'll be able to look at matrices for equations like this. We'll be able to tell if there is a solution, like all three lines intersect, or if there is no solution because the lines don't intersect, or if they are all the same line. And we'll be able to tell that by looking at the matrix. There'll be tricks that'll tell us different properties about the matrix. All right, it's 4:30. Let's take a 10-minute break, y'all. Come back at 4:37, and then we'll try to work some of these examples.
Sorry, sir. My computer died and I had to go get the charger.
That's all right. We're taking a 10-minute break until 4:37.
Okay.
All right, class, welcome back. Let's see. Let's work an example here. So here's a system of two linear equations. It is represented by this augmented matrix. So this is really a 1x and a negative 4x. So we have a 1 and a negative 4. We got a negative 2y and a 5y. So we got a negative 2 and a 5 and a 3, 6. Okay. So for this one, we want to write it as an augmented matrix. Since there's no x's here, this is 0x, right? And we have a negative x, this would be a negative 1, 0, positive 8, and a 3. We have our line, and we have a 27 and a 12. It's not bad, right? Let's look at some more. So linear algebra is not easy, so we're going to take it slow, okay? All right, is 7, 2 a solution to the following system? Well, if we plug 7 in for the x and 2 in for the y, 7 minus 2 is 5, so that one pans out. But what about for the second equation? We plug in a 7 for the x and a 2 for the y. We got 14 plus 2 is 16. 16 is not equal to 1. So it is no, it is not a solution to the following system. It's only a solution to the first equation. So basically you got two lines here. All right. 7, 2 over 7 up 2. That's a point on one of the lines, but it's not a point where the lines intersect. Does that make sense? How to test a solution? You just plug in your x and your y and make sure it satisfies all the equations. All right, let's see. Actually, let's just grab one of these. Solve the system using a valid geometric approach. Well, let's try doing what we did before, where we did substitution, right? If we rewrite this first one, we can rewrite it as y equals 2x. Then we'll plug that in for the y here, right? That'll give us 3x plus 5 times 2x equals 39. All right, so we're getting a third equation by substituting one into the other. And now we solve it. 3x plus 10x is 39. 13x is 39. So x is 3. Now that we know what x is, we plug it in here. 2 times 3 is 6. So the solution is 3, 6. And we can plug the numbers in to check our work. So that's one way of doing it. Okay. The other way is that method by the elimination method. Okay. So we want to, instead of substituting one into the other, let's add or subtract them. All right. So here's two equations. If I take the first equation and I multiply everything by 5, I get this. Now, why did I multiply it by 5? Because now if I add these together, the y's go away. See, I get a 13x equals 39. And I can divide everything by 13 and I got x equals 3. So from these two equations, we added them to get a third equation, right? And then I added these two to get a fourth equation. All right. Now, if we look at our equations, of course, we can plug this in to find y, or we could continue trying to do the elimination method, right? Let's see here. If we want to get rid of the x's instead, if I multiply the first one, everything by 3, I got a 6x minus 3y equals 0. And if I multiply the bottom one all by 2, I got a 6x plus 10y equals 78. I did that because I'm looking at this. Now if I subtract this one from that one, 6x minus 6x is 0x. Negative 3y minus 10y is a negative 13y. And 0 minus 78 is a negative 78. So that tells us if we divide both sides by negative 13, that y is 6. So basically, we're turning our matrix here, we've turned it into this. All right. This tells us that x is 3 and y is 6. Okay. Let's look at 2 here. See, when it's only these two variables, you can always do the substitution method. That's easy, right? But when you have those 3 variables in x, y, and z, it's really hard to do the substitution because you can only get like y as a function of x's and z's, right? Or you can rewrite x as a function of y's and z's. You know, you still got these 2 variables to deal with. So again, this one, we can do the trick we did before with substitution, right? Let's go ahead and do that because it's the easier way. See, we got 2y equals negative 3x plus 3. Divide both sides by 2. I got a negative 3 halves x plus 3 halves. Now that I know what y is, I plug it in here. So now I get a third equation, but it only has one unknown. So if I multiply through negative 5, I get a 15 halves x minus 15 halves equals negative 19. Since we got these halves, what is negative 19 as far as halves? That would be what, 38 halves? So let's rewrite 19 as 38 halves. All right, and let's rewrite 4x as 8 halves x. So 8 and 15 is 23 halves x. If we add 15 to both sides, see 38 minus 15. That gives us 23 halves. So if 23 halves x is equal to 23 halves, all right, that means x is equal to 1. Knowing x is equal to 1, we got 3 halves plus 3 halves is 0. So the solution here is 1, 0. Let's check. If I plug a 1 in for x into this first equation and a 0 in for y, I get 3. So the first equation worked. Let's check the second one. a 1 for x, and a 0 for y. I got 4. 4 is not negative 19. So I did something wrong here. So whenever I'm checking my work and I get it wrong, I don't just erase or throw away the work that I just did. All right? Put a big X, because I want to make sure that I remember. I might do 3 or 4 tries and until I get it right. I want to make sure I don't keep making the same mistakes. So I'm going to work it again and see if I can get my arithmetic correct this time. So I got a 2y equals a negative 3x plus 3. So that means y is negative 3 halves x, right, dividing by 2, plus 3 halves. I substitute that in here, so that gives me 4x minus 5 times a negative 3 halves x plus 3 halves equals negative 19. So if I multiply my 5 through, I got a plus 15 halves x minus 15 halves equals negative 19. All right, this time, just to get rid of the fractions, I'm going to multiply both sides by 2. So I got an 8x plus 15x minus 15 equals negative 38. So I got a 23x equals a negative 23. So I got x equals negative 1. Last time I got a positive 1. All right, I missed a minus sign somewhere. Right here. Negative 38 plus 15 should have been a negative 23. Should have gotten a negative 1. All right, so that was my mistake. But if I plug a negative 1 in up here, I got 3 halves plus 3 halves, which is 3. So negative 1, 3. Let's check our work here. First equation. 3 times negative 1 plus 2 times 3 is negative 3 plus 6. That's equal to 3. Remember last time I plugged in a 1, 0 and it worked out on the first equation? That was just a total fluke. It happened to be on the same line. Okay. Now let's check the second equation. 4 times negative 1 minus 5 times 3. That's a negative 4 minus 15. That is a negative 19 right there. So this is our solution. Let's check Wolfram Alpha. Let's see if we could figure out how to make it solve 2 equations for us. I've never done this, so let's see what it is. 3x plus 2y equals 3. 3x, so 3x plus 2y equals 3. I'm just going to try a comma. And 4x minus 5y. 4x minus 5y equals negative 19. Let's see if it'll take 2 equations and just give us the answer. Check it out. It actually worked. Negative 1 and 3. They even graphed the lines for us. Boom. Right there where they intersect. Negative 1 and 3. So again, I just said solve, put the 2 equations with a comma, and then said for x. All right? It told me x and y, though. I could have probably left out the 4x. What if I just said Solve. There we go. Still gives me the answers. So Wolfram Alpha here will be very useful for you for checking your work. Okay, what about the elimination method? So instead of doing substitution, let's see what we can do. We want to rewrite one of these where we can add one to the other one, all right, to make either the x go away or the y go away. All right, let's try to make the y go away. So if I multiply this guy through by 5 and this one through by 2, I'll have a 10y and a negative 10y. So let's try that. If I multiply this through by 5, I got a 15x and a 10y and a 15. Multiplying this one through by 2, I got an 8x minus 10y equals negative 38. Okay, so these are equivalent. This one's equivalent to that, and this one's equivalent to that. They're the same thing. I just multiplied through by a number. There's no new information. But if I add these, I got a 23x is equal to a negative 23. This is a new equation. All right, it's not equivalent to these two. It's a combination, right? Which I can, of course, rewrite that as x equals negative 1. Okay, so I'm going to keep that one. So that's related to these. We got that by adding these together. All right, we took 5 times this one and added 2 times that one, and we end up with x equals negative 1. All right. The other thing we could have done is instead of getting rid of x, instead of getting rid of y to find x, let's get rid of x to find y. Well, if I multiply this one through by 4 and this one through by a negative 3, I'll have a 12x and a negative 12x. And when I add them, I'll get rid of the x. So this one says 12x plus 8y is 12. This one says negative 12x plus 15y equals, oh hell, what's 19 times 3? 19 times 3 is 57. So if I add these together, the x's go away. I got a 23y equals 57 plus 12 equals 69. 69 divided by 23 is 3. I got a negative 1 and a 3, which is the correct answers. If we're going to put these in an augmented matrix, we have a 3, 4, 2, negative 5, 3, negative 19. Okay? So what we did up here, let's see, in this method, we multiplied the first equation by 4. So if we multiply this row by 4, we got a 12, 8, 12. And then we multiplied this one through by a negative 3. So it gave us a negative 12, 15, 57. We added one equation to the other. So we're basically keeping, which one are we going to keep? We'll keep that one. 3, 2. We'll keep this original one because it's equivalent to that. But this one down here we're going to get from adding these two together. 12 and 12 is 0. 8 and 15 is 23. 12 and 57 is 69. Did I do that right? Yeah, I think I did that right. No, it's 5 o'clock. We'll do more of this next time. I'll have to review it a little bit so I can make sure I get this matrix stuff to you coherently. But for now, I just want y'all to be able to write down this. This stuff over here we'll figure out later. But I do want you to be able to solve these equations by doing substitution and by multiplying through and adding equations together. All right, I know it'll take a while. It is complicated. So let's do our exam. Number 23. Let's see. It was 197. So again, I want you to solve for the exact answer. And let's do this one. Oops. And this one. All right, get them in by midnight. If you don't make it by midnight, get them in as soon as you can. You know, I'll still get you full credit as long as I haven't uploaded the solutions already, which I do just before I grade them. So usually you have longer than just midnight, but try to get it in by midnight. And I will see you all on Thursday.